Welcome to Chapter 5, Section 3, the continuity of derivatives. In the previous section, we proved the mean value theorems and learned how the derivative controls the global behavior of a function. In this short but beautiful episode, we ask a different kind of question. How wild can a derivative itself be? We already know a derivative need not be continuous. But we will prove a remarkable theorem due to Darboux, saying that every derivative still takes all intermediate values, just like a continuous function. This puts a real restriction on which functions can ever appear as derivatives. Let's dive in. Here's the plan for this episode. We first revisit the surprising example from Section 1 of a derivative that exists everywhere, but fails to be continuous. That raises the question of which functions can be derivatives at all. We then state the intermediate value property for derivatives, theorem 5.12, and compare it with the intermediate value theorem for continuous functions. After that, we walk through the proof, step by step. Finally, we harvest a corollary. A derivative can never have a simple discontinuity, only a discontinuity of the second kind. We close with a summary and a preview of L'Hopital's rule. Let's set the stage. Back in Section 1, Example 5.6, Part B, we met a function that is differentiable at every single point of the real line, and yet its derivative fails to be continuous at 0. So differentiability everywhere does not force the derivative to be a continuous function. Next, this raises a natural question. So derivatives can be discontinuous. Does that mean anything goes? Could any function whatsoever arise as the derivative of some differentiable function? The answer is no. Not every function is a derivative. Derivatives form a special class of functions, and this section identifies one property that every member of that class must have. Here's the key fact of this section. If f our prime exists at every point of an interval, then f our prime assumes intermediate values. In other words, derivatives share one important property with continuous functions, even when they are not continuous themselves. Compare this with Theorem 423, the intermediate value theorem from Chapter 4. Before we state the precise result, let's take another look at the example that started this discussion. As you can see on the slide, the function f of x equals x squared times sine of 1 over x with f of 0 equal to 0 is differentiable at every point, and f prime of 0 equals 0. The picture shows the graph of the derivative in red. Away from 0, it is a nice smooth curve, but as x approaches 0, the cosine term makes the derivative oscillate between values near -1 and +1. Faster and faster without ever settling down. The oscillation becomes so rapid that near the origin, the graph merges into a solid band of red. The individual waves are simply too thin to draw. The red dot at the origin marks the value f prime of 0, which equals 0. So the derivative is defined everywhere, but it has no limit at 0. And it is discontinuous there. Notice, though, that the derivative does not jump over any values. It keeps sweeping through them. That observation is exactly what the next theorem captures. First, a quick reminder of the intermediate value theorem for continuous functions. Theorem 4.23 from Chapter 4. If f is continuous on the closed interval from a to b, and c is any value strictly between f of a and f of b, then f actually attains the value c somewhere inside the interval. In the picture, the blue curve is the graph of a continuous function, the dashed horizontal line is the level C, and the red point marks the place x where the graph crosses that level. The proof used connectedness. A continuous image of an interval is an interval, so no values can be skipped. Now for the surprise. The same conclusion holds for derivatives, even discontinuous ones. Here's the main theorem of this section, often called Darboux' theorem. Suppose f is differentiable at every point of the closed interval from a to b, and suppose lambda is any number strictly between f prime of a and f prime of b. Then the derivative actually takes the value lambda at some interior point x. The first bullet notes that the symmetric case works the same way. If f prime of a is larger than f prime of b, the same conclusion holds. The second bullet is the remarkable part. We assume only that the derivative exists everywhere. We do not assume it is continuous, so we cannot simply apply the intermediate value theorem to f prime. Let's draw a picture of what the theorem says. Let's look at the picture. The dark curve is the graph of f. At the left endpoint a, the blue tangent line is fairly flat. The slope there is f prime of a, which is small. At the right endpoint b, the blue tangent is much steeper. The slope is f prime of b. Now pick any target slope, lambda, strictly in between. The theorem promises a point x between a and b, marked in red, where the tangent line has exactly the slope lambda. Intuitively, as we slide along the curve from a to b, the tangent slope cannot skip over any intermediate value, even if it varies in a discontinuous way. Let's now see how to prove this. Before writing the formal proof, let's understand the strategy. Step 1 is a standard trick. Subtract lambda times t from f of part t to get an auxiliary function g. This tilts the picture so that finding a point where f prime equals lambda becomes finding a point where g prime equals 0. Step 2 shows that g dips below its value at each endpoint, so no endpoint can be where g is smallest. Step 3 invokes compactness. A continuous function on a closed bounded interval attains its minimum somewhere, and by step 2, that somewhere must be an interior point. Step 4 is the result from section 2 that at an interior minimum, the derivative vanishes. Chaining these together finishes the proof. Let's first see this plan in a picture. Here's the whole proof in one picture. The green curve is the graph of the auxiliary function g on the interval from a to b. Because g prime of a is negative, the curve starts by heading downward. So just to the right of a, there is a point t sub 1, marked in orange, where g is strictly below g of a. Symmetrically, because g prime of b is positive, the curve rises into b, so there is a point t sub 2, where g is strictly below g of b. So the smallest value of g is not at either endpoint. The minimum, marked in red at the point x, must lie strictly inside the interval, and there the derivative of g is 0. Now let's carry out each step carefully. Step 1. We define the tilted function g of t equals f of t minus lambda times t, differentiating g prime equals f prime minus lambda. Since lambda lies strictly between f prime of a and f prime of b, we get g prime of a negative and g prime of b positive. Our goal is now to find an interior point where g prime vanishes, because that is exactly where f prime equals lambda. Step 2. We claim the left endpoint is not a minimum of g. Look at the difference quotient on the slide. it converges to g prime of a, which is negative. So for t close enough to a, the quotient itself is negative, but the denominator, t minus a, is positive, so the numerator must be negative. That gives a point t sub 1, where g is strictly smaller than g of a. Note the subtle point. We only know the derivative at the single point a, so we cannot say g is decreasing on an interval, but one point below g of a is all we need. Next, the right endpoint. Step 3 is the mirror image. The difference quotient at b converges to g prime of b, which is positive, so it is positive for t close to b. This time the denominator, t minus b, is negative, so the numerator must be negative as well. That produces a point t sub 2, where g is strictly below g of b, so neither endpoint achieves the smallest value of g. Now compactness enters. Step 4. The function g is differentiable, hence continuous, and the closed interval from a to b is compact. Recall theorem Darboux 16. A continuous real function on a compact set attains its minimum. So there is a point x in the interval where g is smallest. Could that point be an endpoint? No. Step 2 gave us a value of g strictly below g of a, and step 3 gave 1 strictly below g of b. So the minimum point x lies strictly between a and b. One step remains. Step 5, the conclusion. The point x is an interior minimum of g, and g is differentiable there. By theorem 5.8 from the previous section, the derivative at an interior extremum must vanish, so g prime of x equals 0. Since g prime equals f prime minus lambda, this says exactly that f prime of x equals lambda, and the proof is complete. Notice how the proof never needed continuity of the derivative. It only used the existence of the derivative at every point, plus compactness. Let's now collect the consequences. To appreciate the corollary, recall definition 4.26 from Chapter 4, which classifies discontinuities into two kinds. A simple discontinuity, also called a discontinuity of the first kind, is one where both one-sided limits exist. The function jumps from one value to another, or has both limits equal but different from the function value. A discontinuity of the second kind is one where at least one of the one-sided limits fails to exist entirely. For example, because the function oscillates. With this language in place, here is what theorem 5.12 tells us about derivatives. Here's the corollary. If f is differentiable on the whole interval, then its derivative cannot have any simple discontinuities. In other words, a derivative can never jump. The key idea is on the slide. At a jump, the one-sided limits of f prime exist but leave a gap, and every value inside that gap would be skipped by f prime near the jump point. But theorem 5.12 says a derivative can never skip intermediate values. Let's make this picture explicit on the next slide. Here is the picture of an impossible situation. The blue curve shows a hypothetical derivative with a jump at the point x. Approaching from the left, the values tend to the lower open circle, the left-hand limit. Approaching from the right, they tend to the upper open circle, the right-hand limit. The dashed line drops from the lower circle down to the point x on the horizontal axis, marking where the jump happens. The shaded pink band between the two circles is the gap. Near x, the hypothetical derivative takes values just below the band on the left side and just above the band on the right side, but nothing inside the band. Now apply theorem 5.12 on a small interval around S6. Any value in the band lies between two attained derivative values, so it would have to be attained. Contradiction, so a derivative simply cannot jump. A word of caution. The corollary rules out only simple discontinuities. Discontinuities of the second kind can and do occur. Our running example 5.6, part B, is exactly of this type. The first bullet recalls its derivative, which oscillates without settling down as x approaches 0. The second bullet points out that neither one-sided limit exists at 0. So this is a discontinuity of the second kind, and there is no conflict with theorem 5.12, because the wild oscillation sweeps through all the intermediate values instead of skipping any. So the picture is consistent. Derivatives may oscillate badly, but they may never jump. Let's summarize. Let's review what we covered. The centerpiece was theorem 5.12, often called Darboux's theorem. If f is differentiable on a closed interval, then its derivative assumes every value between f prime of a and f prime of b, with no continuity assumption on the derivative whatsoever. The proof tilted the function, used compactness to find an interior minimum, and applied the vanishing derivative theorem from section 2. As a corollary, a derivative can never have a simple discontinuity. A jump in the derivative would leave a gap of skipped values, and Darboux' theorem forbids skipping. This is a genuine restriction on which functions can be derivatives. For example, a step function is continuous except for one innocent jump. Yet it is not the derivative of anything on an interval containing that jump. On the other hand, discontinuities of the second kind are possible. Example 5.6, part B, gave a derivative that oscillates so wildly near 0 that no one-sided limit exists. So derivatives occupy a curious middle ground, not necessarily continuous, but never jumping. In the next episode, we put the generalized mean value theorem to work and prove one of the most practical results of the chapter, L'Hopital's rule, which lets us compute limits of quotients by differentiating the numerator and the denominator. See you there.